Okay, welcome back to part 2 of Laplace transforms for section 10.1. So we did a couple of Laplace transforms in the previous video here. So let's try another one. Let's try the Laplace transform of e to the at. Well, by the definition of what the Laplace transform is, it's going to be the integral from 0 to infinity of e to the negative st times e to the at, the function we're trying to take the Laplace transform of, which is going to give us the limit as b approaches infinity of the integral from 0 to b. And then using properties of exponents, they have the same base. So we'll have e to the negative st plus at dt, which I'm going to rewrite as, factoring out the t, e to the negative s plus a times t dt, and we're still doing the integral from 0 to b, okay, which we can now use a u substitution. Let's let u equal, I'll just call it a minus s, and then times t, of course. Then du will be a minus s. Okay, so we've got that guy. So I just wrote the a minus the s instead of s negative s plus a. Okay, times dt. So if we divide by a minus s, we find out that dt is du over a minus s. Okay, so we're going to get the integral, and we still need to do a limit as b approaches infinity. But I'm going to do an indefinite integral first of e to the u, and then in place of dt, I'm going to put in du over a minus s, where a is a constant and s is going to be a constant. So if we do that indefinite integral, we're going to get limit as b approaches infinity of, and then we'll have the 1 over a minus s, and the integral of e to the u du is e to the u. Okay, and so let's do that, and then we're going to have to evaluate him. So let's convert back to our original variable of t. So we're going to do e to the u, which is a minus s t over a minus s, and we're taking the limit of this as t goes from 0 to b, which will take this out, 1 over a minus s times the limit as b approaches infinity of e to the negative a minus s t from 0 to b, okay, which will give us 1 over a minus s. And if we put this in, and if we let t be b as b goes to infinity, okay, if s is greater than a, so let me write that down. So if s is greater than a, that will give me a negative number here. And so e to the negative number will go to 0. And when we stick a 0 in for t, we'll get a minus 1. Or well, we'll get 1 here, but on the evaluation of the limit, he subtract because he's the second f of b minus f of a. So that gives us negative 1 over a minus s, or if I times top and bottom by negative 1, I will get 1 over s minus a. And that will work, provided, of course, that s is greater than a. So, and this guy is the Laplace transform for e to the a t. All right. Again, provided that s has to be greater than a so that the integral will converge. Okay. Now, why do we like Laplace transforms? Well, they have really nice properties and they can help us solve problems. So one of the first things that we notice about the Laplace transform, and it gets it because of the fact of the integral in the definition, the Laplace transform of a times f of t plus b times g of t is, because of the ability to factor constants out and split up integrals over addition and subtraction, a times the Laplace transform of f of t plus b times the Laplace transform of g of t. So that allows us to take harder problems and break them down into more easier to manage pieces. So this is the Laplace transform of 3 minus the Laplace transform of 4t, but we can factor those scalars out. So this is 3 times the Laplace transform of 1 minus 4 times the Laplace transform of t. And we've just done in the last video that the Laplace transform of 1 is 1 over s. And the Laplace transform for t is 1 over s squared. So the Laplace transform for the function 3 minus 4t is 3 over s minus 4 over s squared, which occasionally you'll see written as 3s minus 4 all over s squared, but it's the same thing. Okay. How about this guy, the Laplace transform, or 5 times e to the 2t plus 7t? Well, that's going to be 5 times the Laplace transform for e to the 2t plus 7 times the Laplace transform for t. And we got done doing it just a second ago. The Laplace transform for e to the 2t is going to be 1 over s minus 2 plus 7 times the Laplace transform for t, which is 1 over s squared. And if we simplify that, we've got 5 over s minus 2 plus 7 over s squared. Okay. All right. So what if we needed to take the Laplace transform of t to a higher power, like t squared or t cubed or something like that? Well, we can do that. You do integration by parts lots and lots and lots of times. Or what you can do is use somebody called the gamma function. The gamma function is related to the definition to the Laplace transform. The gamma of x is the integral from 0 to infinity of e to the negative t to the x minus 1. And let's just check and see what happens here. If we pop a x equals 1 in there, we'll have t to the 1 minus 1, which is 0. Okay. And then we'll just have the integral of from 0 to infinity of e to the negative t dt, which we remember from calculus 2 is 1. Now, if we use some integration by parts and some induction, we can show the fact that the gamma function of x plus 1 is x times the gamma function of x. So what does that mean? It means that the gamma function of n plus 1 is n factorial whenever n is a positive integer. Okay, so for example, if we're talking about gamma of 4, that's gamma of 3 plus 1. I know it's a little bit weird, but that gives me 3 times gamma of 2, and gamma of 2 is going to be 3 times 2 times gamma of 1, and we just did earlier that gamma of 1 is 1, so we get 3 times 2 times 1, which is 6, but also notice that that is 3 factorial. Okay. There's a spiffy little applet that I found. There's many of them, but one that I found that you might enjoy is this guy right here at keysen.casio.com slash exec.system slash 118.05734444. And that actually shows you the gamma function. And so you can put in some values here. So if you put in gamma of 4 and execute, so we'll see that gamma of 4 is 6. Okay. And let's do gamma of 6. And we'll find out that that should be 5 factorial or 120. And it even does a graph of the gamma function here. Okay. All right, we'll pick up in the next video and show how we can use the gamma function together with our Laplace transforms.